All right, so this is the second video in section 7.1. We're going to continue to do an example or two where we're trying to find a confidence interval for the mean of a normal population where I know the variance or the standard deviation sigma, okay? All right, so once this thing's settling down in terms of, there you go. Why don't you pause, copy this panel down, then press play. Okay, so let's pretend we have a random sample of 30 2022 Honda Accords, and we test their gas mileage. So we run them through some course and we record their gas mileage. And then let's say some statistician does a 95% confidence interval and it's calculated to be 29.5 to 33.4 miles per gallon, okay? I then have three possible meanings somebody might assume about that confidence interval, and we'll just dissect each one. So the first possible meaning is we are 95% sure that the gas mileage of a 2022 Accord is between 29.5 and 33.4 miles per gallon, okay? This statement is false, okay? The confidence interval refers to where we think the population mean is, not an individual vehicle. It's got, virtually nothing to do with an individual vehicle. So the confidence interval is for the population mean, not for an individual vehicle, person, whatever, okay? Another possible meaning, 95% of all 2022 Accords will give an average MPG between 29.5 and 33.4. This is also false. The confidence interval means that each sample of 30 Honda Accords yields its own confidence interval, and 95% of these confidence intervals will contain the population mean mu, okay? Not that 95% of the vehicles will land within that zone. Possible meaning three, there's a 95% chance the true mean of the 2022 Accord, the true population mean that we're after, is between 29.5 and 33.4. This is the most seductive explanation. And unfortunately, it is false as well, okay? The true population mean is fixed. We don't know it, but it's a fixed number. So it's either in this interval or it's not. So the probability that mu is in this interval is either 0 if it's not in the interval or 1 if it is in the interval, okay? It's not 95%. Okay. Why does it do that? It should stay there. Okay, so important question to look over, especially as exam time comes along, just to make sure you understand what a 95% confidence interval is really telling us. Okay, second panel. All right, pause, copy, play. So to repeat, in our confidence interval formula from the first video, we called the quantile times sigma over root m the margin of error, all right? So let's use that margin of error, the MOE. Let's say we wish to estimate the mean weight of those 13-year-old girls and have a 95% confidence interval with a margin of error of at most 5 pounds. So that's the zone I want to have, a plus or minus 5 pound confidence interval. What sample size is required? Okay, well, that 5 pounds is referring to the margin. So I want 5 to be at most greater than or equal to the margin of error, Q times sigma over root m. It's a 95% confidence interval, so my Q value is 1.96 as it was in the first video. I know my sigma was 24.6. I'm not sure about m. That's what I'm trying to solve for. So I've got 5 is greater than or equal to this quantity. I can multiply the root n over, divide the 5 over, square both sides, and I get n has to be greater than or equal to 92.99. So I need my n to be at least 93 13-year-old girls' weights that I use in my data set to get a confidence interval whose margin of error is at most 5 pounds. Okay? And if you note, if you look back at the confidence interval that we did, when we had an n of 150, our margin of error was definitely less than 5 pounds. Okay, so that pretty much covers confidence intervals for data that's normally distributed when we know the standard deviation or the variance. So we're moving on to the second scenario that was referred to in the first video. So why don't you pause, copy, and play. All right, so the second scenario is that we've got normally distributed data still, and I still want to get a confidence interval for my unknown population mean mu, but this time sigma is not going to be known. Okay, so this is scenario 2. By the way, mu is unknown as well. That's why we want this confidence interval. So we're going to continue to use X bar as an estimator of mu. And now I don't have sigma, the standard deviation, so I'm going to use the best unbiased estimator of sigma that I've got. And that was S, the sample standard deviation or standard error. Okay, and if you remember, it was the square root of 1 over n minus 1 times the sum of xi minus x bar quantity squared. All right, and in the last chapter, we showed that this was an unbiased estimator, sigma. So let's use it, okay? Well, okay, we could happily try that, and what people did for many, many years, and eventually a few people started to realize that this x bar minus mu divided by s over root n, that standardizing procedure we did in the last video with sigma instead of s, they realized that this thing is not quite standard normal. It's got slightly fatter or longer tails, depending on how you want to think about it, okay? It sort of spreads out a bit more than a standard normal distribution does. Though the good news was, as your sample got really, really large, this fraction did approach standard normal behavior. So that was good. And if you look on page 195, figure 7.4, they compare this distribution to the standard normal distribution, and you can see they're just sort of slightly off. All right. Well, okay, so late 1800s, early 1900s, around 1900, there's this statistician working at Guinness Brewery in Dublin, all right, named William Gossett. And what they're doing is they're weighing these, they're receiving these bags of barley, and they're all supposed to weigh, I don't know, 10 pounds, who knows what, right? But they don't, right? Some are a little bit more, some are a little bit less. And so William Gossett is trying to sample a few of the bags and figure out whether the farmers who are selling him the bags are systematically underweighting the bags from what they're supposed to be, right? Is Guinness Brewery getting cheated because the farmers are, pulling a few ounces out of each bag or something, right? Now the problem is his N, the number of bags he's sampling, isn't too huge. He doesn't want to sample 5,000 bags, or in other words, that would just be sampling all the bags in the brewery. So it's just weighing each and every bag, and that would take a long time and slow down the intake of barley they need to brew. So what he did with his small values of N is he gathered a bunch of data, and then he created a new distribution to describe this this quantity X bar minus the true population mean all over the standard error divided by root n. And it was a better match than N01, so it provided better results. Now, Guinness wouldn't let him publish this new distribution unless he anonymized it. So in 1908, Gossett published this in a stat journal in the United Kingdom or in England, and he listed as his name student. He wasn't allowed to use his new name because otherwise, or his actual name, sorry, because then people would realize that Guinness Brewing was using this, and other brewers might steal it, and then competitive advantage would be lost for Guinness. All right, so he published under a pseudonym student. So this distribution, we nowadays call it the T distribution, but you might have heard it referred to as the student T distribution. And in the next video, we'll delve into this distribution and how we use it.